So we have the third of Fabio's lectures, and just remind you, in case you're new, though probably you're not, if you have a question, just unmute yourself, or you can put it in the chat. Just make sure to chat everyone so that, well, we can all see the question. Fabio might not see it in any good time. And also so other people can answer your questions for you if Fabio doesn't need to. Okay, anyway, Fabio, take it away.
Yes. All right, thanks. So I will start by recapitulating a bit where we got. And so the goal today would be, yesterday I gave you some of the tools, some of the basics we use for our main result, and today I would like to explain the strategy of the proof. So let me recapitulate. So we are looking at this stochastic partial differential equation. You see here this anisotropic AKPZ equation. So it's defined for, okay, there is time, h is a function of t and x, time is time, and x is in the torus. We reduced ourselves to the torus of size 1. Initially, we were interested in large scales, but by a simple trick, we reduced to scale 1. I mean, this is just for notational convenience. And you have the derivative, time derivative of h equals the Laplace, half of the Laplacian, plus psi, which is the space-time white noise, plus lambda times, and lambda will be a real value. I mean, the interesting case is non-zero. Positive or negative doesn't make any difference, but just think of lambda. Positive doesn't need to be small for our result. By the way, it's not a perturbative result. The result is true for any lambda. Okay, and then there is this nonlinear terms that I denote NL of h, which again is defined as follows. Formally would be defined as derivative of h with respect to x squared minus derivative of h with respect to y squared. This is what D1 and D2 mean, except that you have to regularize this term, and the way you do it is in Fourier space. Before taking the derivatives of squares, you apply this operator PL to the function, where PL just means it puts to 0 all Fourier modes with index k larger than L in say, Euclidean norm. Okay, so this is the regularized nonlinearity. And very good. So the thing I showed yesterday is that if you start your h from a Gaussian free field on the torus, that is stationary. So at all fixed times, you will the law of your interface will be the Gaussian free field. And then I did a few steps, more or less in detail, to rewrite what we call the bulk diffusion coefficient in a more helpful form. So this d bulk TL, so it depends on time, it depends on the scale L, on this parameter L, and it's given as follows. So you give them by 1, which is the value it takes for the linear equation. Then there is a plus lambda square over t. So it vanishes when lambda equals 0. And then you have the expectation with respect to this stochastic process of what? Well, you have to take the nonlinearity NL. First, you integrate it on the torus. So you're taking the zero Fourier mode of the nonlinearity. So you integrate n over the torus, so dx. Then you integrate it in time, from time 0 to t over L squared. And then you square this thing. So you're taking the variance of the time integral of the zero Fourier mode of the nonlinearity. Okay, so getting from our definition to here is just trivial manipulations. There is nothing serious. Okay, so the goal in principle, so here I put some quotes, the goal is to prove that this diffusion coefficient diverges in time like log t to some power. And as I already said, in practice, we prove this in the sense of Laplace transform. So we take first the Laplace transform of this quantity, where for convenience, purely for notational convenience, I multiply by mu this integral, which is not the standard notation, but it's somehow more convenient. And then we take actually the Laplace transform of t times the bulk diffusion coefficient. All right. Okay, so good. So now the precise goal is actually to prove that as this parameter mu goes to 0, which corresponds to large times, this Laplace transform behaves like 1 over mu. 1 over mu would correspond to the case where d were just constant. 1 over mu times a logarithmic correction, log 1 over mu to the power 1 over delta, 1 minus delta, or delta according to whether you want upper or lower bound. And again, we want to have this for mu small, but first we will take L to infinity. So we take the limits in this order. Okay, so very good. So what we have seen last time at the very end was that it is possible to write down this Laplace transform of the diffusion coefficient in terms of the inverse of the generator. So LT here denotes the generator of the equation. So it depends on L because L appears in this cutoff in Fourier space. Okay, we have seen that this d mu can be written as 1 over mu times, okay, the one, I mean, stays, no problem. Then there is the expectation of NL times the inverse of mu L squared minus Ln times NL. So again, NL is simply the 0 Fourier mode of the nonlinearity. So it's written here, it's an integral on the torus of the nonlinearity computed at x, integrating in dx. Okay, and then you have to sandwich this thing. I mean, you have to sandwich the mu L square minus the generator inverse between NL and NL. And then take the expectation. And this expectation now is an expectation as a single time. The time integral has disappeared, has been done with this small trick here that I said last time. When you take the Laplace transform, you have a e to the minus mu t plus LT, which comes from the semigroup. When you integrate that in time, it gives you an inverse of mu minus L. That's all. That's all what is behind this. And this inverse exists because, I mean, the generator is his eigenvalues have negative real part, mu is positive, so there is no, I mean, there is this formula is well posed. There is no problem. But of course, the point is to estimate how does one see the log divergence here? It's a priori it's not so obvious. Okay, so here is where we stopped last time. And before I actually start with the real work, let me make two historical notes about this result. So the first historical note, okay, I will mention two related results. One of them is related in the sense that it's morally related, in the sense that the problem is quite different, but the techniques are close in a sense. So our method is inspired exactly by the techniques in the paper I'm going to mention. And the second related problem I want to mention is very related is very similar problem, but the techniques are very different. So let me come to that. So the first thing I want to mention is two papers. The first one by Landim, Castel, Salmofer, and Yao, and the second by Yao himself, where they looked at the asymmetric simple exclusion process on Z1 or Z2. And I'm thinking especially of the case of Z2. And what actually was proven in the second paper is that the diffusion coefficient, that I will redefine in a second, but it's defined similarly to what we are doing now, diverges in dimension 2 as logarithm of time to the power 2/3. Okay, so it's quite similar. In our case, we also have a divergence, logarithmic divergence of the diffusion coefficient for AKPZ. Again, also in Yao's case, this is proven in the sense of Laplace transform, the same as for us. And notice that in that case, in Yao's case, this exponent of the log is 2/3 and not 1/2, which is presumably conjecturally the exponent in our case. So if you apply the same heuristics we use to get the 1/2 to that case, which is something that was done by Spohn long ago, you get the 2/3. So with the same heuristics, you get the two different conjectures. It's not like we're using a different argument and then maybe we're missing something. So it's really the same heuristics gives in the two cases a different exponent. And so what is this process I mentioned? So probably you can imagine. So you are on Z2. On Z2 you have particles So at most one particle per side. Sometimes you have a particle, sometimes you have a hole. So let's say this is okay. And then the particles, each particle independently tries to jump to one of its neighbors. And the case where they prove, and okay, so the specific case they prove the result is where the rate of jump, of course, you can never jump on an unoccupied site. This is the exclusion rule. And what the case they consider is that with the one where on the horizontal direction, the process is totally asymmetric. So you have a rate of jump 1 to the right and 0 to the left. And on the orthogonal direction, you are symmetric. Okay, so they consider this special case of where the asymmetry is total and is only in one dimension, in one direction. Anyway, so maybe this is not essential. Okay, and then what they do, they define the bulk diffusion coefficient similar to our case. So they start their measure from the Bernoulli 1/2, which is stationary, and then they compute. They consider something like you take the occupation variable, so like particle or no particle, at xt minus 1/2, which is the average value, times the same thing at 0, 0, minus 1/2. Then you want to sum this over x and multiply by x squared. So at time 0, this expectation is, since Bernoulli is the equilibrium measure is IID Bernoulli, this at time 0, this expectation is zero only, is non-zero only if x is 0. Okay, so it's a Dirac, it's a Kronecker-Dirac Kronecker function, but at later times it's not. And then you want to define this quantity, which again they call the t times the bulk diffusion coefficient respect to t. So it's really analog to what we do, except in our case we don't have occupation variable. There are no particles for our equation. We have something like we had the expectation of the function utx u0, 0, where u was just the solution of the equation where when you apply the minus Laplacian to the power 1/2. So, but other than that, it's quite similar. As I promised, I mean, this definition of bulk diffusion coefficient is similar to what is adopted in usually in particle systems. Okay, very well. So the second thing I wanted to mention is an analog of our result, but in one dimension. So in this paper by Balázs, Castell, and Sepalainen, 2011, what they looked at is the KPZ equation in one dimension. And what they prove is that the diffusion coefficient d of t diverges with time, this time not logarithmically, but as it should as t to the 1/3, upper and lower bound. So here they don't need to go to Laplace transform, if I understand well. And so in principle it's quite close. It's really the analog of what we proved for the 2D case, except that a big difference here is that in this case, they have an underlying particle process, which is the weakly asymmetric process, weakly asymmetric exclusion process. And it's important to use that this process approximates the KPZ equation. In our case, unfortunately, we don't have any particle process for which we can prove that it converges to anisotropic KPZ, at least yet. So we cannot use anything from directly from the particle system. We have to work directly with the SPD. Okay, so these are two historical notes it was important to make. I think let me check if there is no question. So let me proceed. All right, so now really I have no excuse. I have to explain how things work. So right, so the main thing is to estimate to bound above and below this type of expectation with respect to Gaussian free field of this nonlinearity times this inverse of mu minus L times nonlinearity. So here for some time I'm dropping the index L. In principle, there should be an index L in the generator. There is an index L in the nonlinearity because the cutoff in Fourier space is at L, and this mu should be mu lambda square, if you remember what was written here somewhere. Yeah, I don't know where it is, but yeah, it was in this page. You see, we have to compute the things at mu lambda square, not at mu L square, not at mu. But for the moment, I mean, for some time, I will if you want, call mu L square, call it mu. Okay, so in principle, this might look easy in the sense that in principle, what you should do is to solve this equation. So suppose you can find a so it will be a random variable phi, which solves mu minus the generator applied to phi equals the nonlinearity. So this is the same n that appears here. This equation in principle can be solved because mu minus L can be inverted. Now, if you are able to find phi that solves that, then you are done, because then your expectation En E inverse n is just equals to En times phi. I mean, by definition. No? And actually, it's even better than that, because remember, any function phi in L2, any square integrable function of the Fourier modes can be expanded in Wiener-Chaos decomposition. So phi can always be written as a sum from 0 to infinity of phi n, where phi n belongs to the nth Wiener-Chaos. So if you want, onto the Fock space of order n. But now you are multiplying here by n, large n, not the order of the chaos, and that n there belongs to the second chaos. Okay, n is bilinear. The linearity is only quadratic in the fields. It belongs actually to the second chaos. So when you take this product n times phi, all you care about is the component of phi which is in the second chaos. All the others don't matter. They give 0 in this expectation. So in the end, all this complicated thing you want to compute is just the expectation of n times the second component of phi, where phi again is the solution of this equation here. And in principle, well, and not just in principle, phi has components in all causes of order n. Okay, but if you are able just to find the second component, everyone is happy. You can compute the expectation, and that's over. Okay, of course, what makes things complicated is that when you write down this equation, so actually it's an infinite set of equations, one on each, if you project on every chaos of order n. So let me see, there is a question here. Marker, which marker? Okay, so I will try to,
I guess to distinguish from what's already written.
Green, yeah, good idea, thanks. Okay, yes, okay, so this equation which looks, this equation here actually is not one equation. If you want, it's an infinite set of equations if you project it on the different causes Hn. So let's see how it looks like. Well, okay, so first I wanted, just for those who maybe forgot, to recall this chaos decomposition. So the fact is that L2 of eta can be written as an orthogonal decomposition of this Hn, and each Hn is spanned by the so-called Hermite polynomials of order n, which I denote with this notation of Wick products, eta k1, eta up to eta kn with these double dots. It just means that this thing has been made orthogonal to all the causes of lower order. And then every function f in L2 can be written first as the decomposition, as a sum over the order of the chaos. And then once you fix that order of the chaos n, then you have a sum over the indices J1 up to Jn, which run in Z2. These are simply the variables in the Fourier decomposition of a function. So you can view this as a kernel phi n J1 up to Jn, which has to be it's symmetric, because otherwise the anti-symmetric part would anyway give no contribution, times this Hermite polynomial. Okay, so this is the general decomposition. Of course, if you want the function to be in L2, these kernels will have to decay well in N and also in J, so that everything is summable, square summable. Okay, so this was just a small reminder of this decomposition. All right, so as I was saying, the equation for phi is actually an infinite system of equations. So if you write down that the generator L is, as we discussed last time, is a sum of the generator of the linear equation plus the part of the nonlinear equation, lambda times A, and A itself can be written as a part A plus that lifts by 1 the order of the chaos and one that lowers it by 1, A plus and A minus. By the way, from now, for some slides, I will forget the lambda. Let's put lambda to 1. You just forgot to write it down. Okay, so if you remember that the generator was decomposed that way, and also that L0 preserves the order of the chaos and A plus minus lower or increase or decrease it, actually you get an infinite systems for these components phi n of the function phi. Okay, for instance, if you project on the first chaos, you get the nu minus L0 phi 1. I will maybe work out a little bit more of this in the next slide, but let me just say what comes out. So the component of phi in the first chaos satisfies mu minus L0 applied to phi 1 equals A minus phi 2. Okay, so phi 1 is expressed as a function of phi 2. Now you write down the equation for phi 2. It's mu minus L0 phi 2 minus A plus phi 1. Notice that phi 1 is in the first chaos, so A plus phi 1 is the second chaos, good. Minus A minus phi 3, which is also in the second chaos, equals the nonlinearity, which is in the second chaos. So this is the component of the equation in the second chaos. And phi 2 is the one we are really interested in, but unfortunately it depends on phi 3. And then you go on, mu minus L0 phi 3 minus A plus phi 2 minus A minus phi 4 equals 0. And then you go on. I mean, you want phi 2, but for phi 2 you need phi 3, for phi 3 you need phi 4, etc. So this is what makes the problem complicated. And it's, of course, it's not a new phenomenon. I mean, I don't know if you are looking at, okay, if any of you knows, but if you look at kinetic problems of particles interacting and you want to derive somehow Boltzmann equation or something like that, there is a similar hierarchy of equations. For if you want to describe the marginal distribution of n particles, it turns out to depend on the distribution of n plus 1 particles and so on. Okay, so it's hard to close. You don't get a closed equation for each one of these. Like here, I don't get a closed equation for phi 2. Okay, so in that case, I mean, either you argue somehow that when you go with n larger and larger, at some point things can be neglected. That's a possibility. Or maybe it so happens that at some point the equations magically close. Or otherwise, which is the way that works in our case, you can resort to some truncation. So somehow you replace your infinite system by a finite system, finite but large, and then hope that in the limit where the system becomes large, then you get what you want. Okay, so let's see how it works. The way, and this argument is inspired by, is very similar to what Landim and others do for the asymmetric simple exclusion. It's a truncation argument. That is, you replace your generator L, which is complicated, by a truncated generator where you pre and post multiply this generator by Pn. This P smaller equal n, it just means this P smaller equal n is simply the orthogonal projection over all the over the causes of order 0 up to n. So when you take this truncated generator, you apply to some function. So first it projects on the causes up to n, then it applies L, and then it reprojects on the causes up to n, because once you apply L, you could have a component on n plus 1, which you want to kill again. Okay, so it's really a truncated thing. It's like forgetting all the causes of order n plus 1, n plus 2, and so on. And so now the idea is, well, let's look for this similar equation, except that now I take L, the truncated generator, instead of the full one. And of course, the solution phi n will not be, will depend on n, of course, no surprise. Now, the point is, there are two things which are interesting. First, it becomes a finite system, of course, essentially by definition. And the second thing is that this solution is actually usable as a bound. Without this second dot, this procedure would not be so useful. But the important thing is that the true thing we want, this E expectation of n times phi 2, is upper bounded by the truncated equivalent, the analogous truncated quantity, if the order of the truncation is an even integer, and is lower bounded by the same thing if n is an odd integer. So Good. So this is not only provides you a finite system, but if you can solve that finite system, you get bounds which are in both directions according to whether this order of truncation is even or odd. And the other thing you can prove is that as n or m go to infinity, these two bounds are better and better. They approach if you take n or n plus 2, you get two upper bounds which are one better than this. So the upper bound with n plus 2 is better than the one with n. And these two lower and upper bounds approach each other and converge to the true value as n going to infinity. So there is really we're really in the good situation to use these bounds. So we know a priori that they converge to the good thing. So now the point is to somehow okay, I mean, the problem is not solved. I mean, you have now to do something with these truncated equations. Okay, very good. So let me work out more explicitly how this finite system looks like. So now maybe I rewrite in black. Okay, so you want to solve this mu time minus ln phi n equals n, where n belongs to the second cause. And sorry, this is a 2. And now, okay, so you want to write down all the components that corresponds to this equation, corresponds to from the cause 0 to n. And actually, it's convenient to start with the highest cause. So if we project on the, so suppose n is larger than 2. So if we project on the nth cause, the right-hand side gives 0 because n is in the second cause. And the left-hand side would give you, okay, so this would be the first equation, would give you mu minus L0 phi n component n. Okay. And then what? And then, yeah, minus a plus phi n component n minus 1, because when you apply phi a plus, that goes to the chaos n, and then nothing equals 0. The a minus will not act because it should act on the, to give something on nth chaos, it should act on the n plus 1th, but there is this projection which kills that part. Okay. So this is the first equation starting from the highest chaos, and then you go to the next one, and what you get is mu minus L0 phi n minus 1 minus a plus phi n minus 2, which again is in this n minus 1th chaos and first chaos. And now there is another term which is a minus phi n and that's it, equals 0. So because this time phi n, when you apply a minus, is in the chaos n minus 1. And then you go on. I mean, notice that, okay. And then you go on, you reach the chaos 2, you gives you mu minus L0, I'm copying, otherwise I will never write it correctly, minus a plus phi n1 minus a minus phi n3. Now, the right-hand side gives you n, because that is in the second chaos, and then there is a final last equation, which is mu minus L0 phi n1 minus a minus phi n2 is 0. Okay, so now it's still a complicated thing. I mean, these are all operators, this mu 0, a, etc. Not mu 0, but L0. So it's not obvious, but at least it's a finite system. You can solve it starting from the top. Okay, and the way you solve it, it's quite. I mean, in principle, it's quite simple. I mean, you look at the first equation, and the solution is you see it. I mean, what is phi n? You simply move to the right-hand side a plus phi n minus 1, and then you invert the operator mu minus L0, which is an easy operator. It's just the generator of the linear equation that we can invert. As I said, in Fourier space, it acts simply as a multiplication by mu plus k squared. So the inverse is just dividing by mu plus k squared. So this is something we can do. So, okay, so how does the solution to this system look like? Well, the first one is easy. Okay, so you get that phi n is simply mu minus L0 inverse times a plus phi n minus 1. Of course, phi n minus 1, we don't know yet what it is, but it will be done iteratively. And then we go to the second equation. I will not do more than 2, but I guess now it's clear what one does. You get this. The second equation is this. A minus, now there is a minus times phi nn, which you have just computed. So you get this mu minus L0 inverse a plus phi n minus 1, which is, I mean, phi n minus 1 is the one for which we are trying to solve. And then equals on the right-hand side, you get a plus phi n minus 2. So if you solve this, it just gives you that phi n minus 1 is what? Is the inverse. It gets, of course, the more you proceed, the more it gets complicated and difficult to write down, but there is a very simple iterative way to write it down. Minus a minus mu minus L0 minus 1a plus applied to what? Inverse applied to a plus phi n minus 2. Okay, so now we have solved somehow the second equation, and then you go on. Okay, you can imagine you go on, and this stops after a finite number, after n steps. I mean, there is nothing that continues to infinity. And all these inverses I'm writing down are well posed, because this operator is positive, and this operator we'll see in a second, it's also positive. So these inverses pose no problem. Okay, so if you iterate n times this procedure, what you get, remember, the only component we really care about is the second component. For the second component, this is what you find. You get the inverse of this mu minus L0 plus this Vn, which I will define in a second, plus this extra operator here. Let me use the green here. This extra operator here comes from the first equation, the equation for the first chaos. This is an operator that I can just describe as annoying, because it's annoyed as a lot during the proofs, but okay, it is there. Inverse applied to n. And this is a solution of your system, the only component we care about. And these operators Vn are defined iteratively. The first one, V3, is just what appears here. Where is it? Essentially is what appears exactly. It's exactly what appears in the second equation I've written down. Minus a minus mu minus L0 inverse a plus is exactly this V3. And then when you continue this procedure, you will have more and more complicated operators, Vk, which are defined iteratively in terms of Vk minus 1. And the definition is here. Okay, so in a sense, this is the solution of the system. But of course, it's not yet in a form where you can see any bound or of any kind. So this is not yet really the work. This is still the preparation. So a few observations. So all these operators involve both the generator of the linear equation and the nonlinearities a plus and a minus. So this is what makes it complicated. If it just involved L0, we would be done. They would preserve the order of the chaos, and they would be diagonal in Fourier space. But because of this a plus and a minus, this operator mix up both the order of the chaos and the momenta. So they are still complicated objects. Okay, very good. So right. So actually, let me come to what is actually the main statement. I mean, it's a technical statement. If you see it isolated from the work, it doesn't make any sense. But it's really where most of the work is concentrated. It is in this recent paper with Giuseppe Canizzaro and Dirk Erhardt. So the point is to have iterative bounds on this operator Vn. And let's see how these bounds look like. Okay, there is some constant depending on lambda. This constant, unfortunately, is larger than 1. I will comment in a second why I say unfortunately. Such that these operators here, and now I've put back the dependence of L because I had removed it for notational convenience in a second ago. The operator with, remember that this operator, according to whether they have an even or an odd index, they will provide upper or lower bounds. So we have somehow to treat them differently. Okay, so the first part of the bounds tells you that the operator with odd index are upper bounded by this constant to the power 2k minus plus 1 times the generator of the linear equation times something that I will define in a second, but that is a function of the generator of the linear equation. Okay, so it's important that in this. So first of all, these bounds have to be interpreted as, I mean, both right and left hand side are operators. They are symmetric operators, so they are in the sense of quadratic forms. They are not numbers. The other observation is that the while the left-hand side involves this A plus, A minus, all this mess, the right-hand side only involves the generator of the linear equation. This is good, because once you get this, life becomes easy. And the lower bound for the operators with even index, we get a similar expression, except it's lower bound. And okay, it's something like a constant to the power minus 2k minus 2. So this constant, unfortunately, gets worse and worse as k grows. And then a certain LB of order k minus 1 of this, so which I've not defined yet. I will not give a full definition, but a kind of impressionistic definition. Apart from details, these LBK and UBK, which appear here, look as follows. Let me write it down as function of a real variable. In practice, you will have to compute them. We put as an input and the Laplacian, but okay. So how does LB at order k of x look like? It's the sum for j smaller or equal than k of, you have to take the jth power of log 1 over epsilon, 1/2 log of 1 over epsilon, divided by j factorial. So look, if the sum were extended to infinity, this would just be an expansion of the exponential. And I will comment on that in a second. While for the upper bound, how it looks like is the log of 1 over the argument divided by the lower bound. Okay, so it may look a bit weird. So for instance, if k equal 1, the upper bound, which is written above here, okay, for the first non-trivial thing, well, I mean, if k equal 1, this ub, for instance, ubk of mu minus L0 divided by L squared is simply, if you read this thing, would be the log of the argument, blah, blah, divided by LB with index 1 is simply the first term in the sum, which is, apart from the 1/2, is log. So the first upper bound is something like log divided by log, for instance. And then, I mean, as k grows, this becomes more and more complicated, because as k grows, you get log, say, squared, third, etc. So somehow the terms you are adding are more and more are bigger and bigger, because you get logs to some power. But on the other hand, you are divided by j factorial. So I mean, it's not so obvious. Okay, anyway, so as I was saying, the good thing is that the bounds only involve the L0, which is good. They are for now diagonally in Fourier space and also in the order of the chaos. And the proof, as you can imagine, since these operators are defined iteratively, also the proof will be iterative. I will only give the hint of how to prove the first one. Don't be scared. And what else? Another remark, yes. Another remark is that if you look a bit at these two equations here for LB and UB, you see some hope. I mean, you see somehow our conjecture delta equal to 1/2 appearing. What do I mean by that? So is that okay? Formally, if in this definition of LB and UB you send k to infinity, as I said, you are just reconstructing the definition of an exponential. You get the exponential of 1/2 log, which is well known to be simply the square root of log. So as k goes to infinity, this lower bound just tends to log to the power 1/2, and the upper bound too, because it's just log divided by lower bound. So log divided by square root also gives square root of log. So in a sense, when k goes to infinity, these bounds, these two bounds tend to the same bound, if it were not for this prefactor c to the power k or minus k. So if somehow by miracle this c were 1, the two bounds would just converge as k goes to infinity, and it would be easy. So, and this 1/2 here would just correspond to the conjecture that we can 1/2. So somehow the form of the operators suggests already that this conjecture should be true. Of course, we have now heuristics that it's much better than this. Okay, so this is about this is the main technical result from which everything then follows. Yeah, as I said, unfortunately, this constant is from the proofs we get something larger than 1. As I said, given these bounds, the main theorems follow easily. I mean, why is it easy? I mean, it still requires some work, but at the end, you have just to, anyway, so these bounds anyway are very explicit in a sense. So in this sense, it follows easily. And another observation is that which makes the problem a bit more difficult than what than the case of the asymmetric simple exclusion in 2D, where Yao proved this log to the 2/3 case. So in Yao's case, you also have an iteration which is a bit like this. But what makes it a bit simpler is that if you want to prove, well, maybe you don't want to prove log to the power 2/3 for the correction. You want to prove log to the power 2/3 minus 1/1000. Okay. In this case, you have just to run your iteration a number of times, which is finite and is just large with this 1/1000. Okay. If you want 1/1,000,000, you have to run a bit more. But in our case, even just to get log to some power, even to get log to 1/100, you have to run this iteration infinite many times. So infinite many means you have to run a number of times which is diverges with epsilon. So this makes things more complicated. So while in Yao's iteration, at every step, you improve the power of the log, here somehow in every step you gain a log-log. So there is a very long way to run to go from a log-log to a square root of log. Okay, so this is a kind of technical comment that you might appreciate if you ever read the paper. And okay, so how? Okay, let me see how. Yeah. Let me try to give at least the idea of how one proves these things. So, of course, the natural way is to proceed by induction. Since the operators themselves are defined inductively, that's a natural way to proceed. So remember, V3 is defined explicit, the first one. So there is no V2. The V3 is the first one, is defined like that. And then V4 is defined by like A minus mu minus L0 plus V3 inverse A plus, blah, blah, okay? Now, the first observation is that all these operators are positive. This is because the A minus and E plus are not the adjoints one of one another, but minus the adjoints. So for instance, if you take, say, V3, you sandwich it between phi and phi, here you would have E of minus A minus phi mu minus L0 inverse, sorry, phi, but now you, I'm sorry, no, this is not what I want to do, sorry. Suppose I want to do phi and then minus A minus mu minus L0 inverse A plus phi, which is like taking V3 sandwich between phi and phi. Now you can move this A minus on phi, it becomes A plus and it loses the minus. So it simply becomes A plus phi, mu minus L0 inverse, A plus phi, which is clearly positive because the operator mu minus L0 is positive. Was there any question, or maybe it was already answered? Okay, so I assume the questions was already answered. Okay, so these operators, at least they are positive, so there will be no problems inverting these things. Okay, but this is, and now in which sense the proof is iterative? Well, suppose for V3 you have proven some upper bound that it locally, let me call it U3. I mean, I'm not specifying what it is. This will provide a lower bound now on V4. Why? Well, if you take V4, this is minus A3. Now we have to invert mu minus L0 plus V3 and then multiply by 5 by A, and then apply A plus. And now if you know that V3 is something smaller or equal than something else, since morally this V3 appears in the denominator because you are taking the inverse of this stuff, you can lower bound this V4 by replacing V3 by U3. This would be totally trivial if you had just numbers, but I mean, also with quadratic forms, that this works for quite well. So, somehow the scheme is you first prove a first upper bound on V3, that gives you a lower bound on V4, that gives you an upper bound on V5, etc. You kind of ping pong up and back and forth between uppers and lower bounds. And the point is just to do it well enough so that they don't give you, they give you something useful. So actually, most of our work, most of the several past months, we spent finding the correct iterative statement, the correct inductive statement that would allow to get the bounds we want. We had many failed attempts. Like for instance, we tried at some point initially to replace this kind of complicated definition by just a last term, which looks like you just take the term over the j equal k, which looks like the most singular. Then the iteration doesn't work. So I mean, and still even okay. Anyway, so we spent the lockdown trying many iterations, and in the end we found the one that works. I would like just to give you a small hint of how things are done. I will not bore you with too much things. Let me say, yeah, well, okay. I would just like to give you a hint of how one proves that this bulk diffusion coefficient diverges at least as a log-log. Okay, then we have much better, but at least a log-log. So, okay, are there any? No, there are no questions. Okay, so let me restart. Then what we want to study is this expectation, which equals the expectation of the nonlinearity times the true phi2. But we know this is larger equal than the truncated problem if m is an odd number, as is written here, and the first bound we can get is by taking the first one, the first non-trivial one will be obtained by taking m to be 3. Okay. Okay. So okay. So now we take m to be 3. M is this upper index of the truncation, but still you want to compute the component in the second chaos. So you are interested in phi 3 component 2, and if you apply our previous definition, this is given by this complicated operator inverted, which contains this v3 applied to the nonlinearity. There is also this annoying thing encircled in blue. Forget about it. You can, but for the purpose of the lecture, let's just forget its existence. And then, okay, so what we, by forgetting this part, what we get is that the thing we are interested in is larger equal than this other stuff. And so how one gets the first non-trivial lower bound that already tells you that the system is super diffusive, very weakly would just give you a log-log, but still, is as follows. So you want an upper bound of V3. If you see our statement on the lower bound, on the upper bound, the upper bound on V3 is simply that V3 is bounded as an operator by the generator of the linear equation times a log of mu minus L0 over L squared. Okay, which is this what I called earlier this UB index 0. Okay, this is one thing. I will not really show how this is done, and then, but I will show how once given that how you obtain the first non-trivial lower bound of log-log for this left-hand side. Well, I mean, how you get this upper bound? I mean, you have to prove it. I mean, you have to take the left-hand side and right-hand side sandwich by taking any possible phi in any chaos. You have to take the sandwich left and right-hand side. You have to check that the left-hand side is small. I mean, it requires work, but I think at this time it would be a bit too demanding for the audience to do this work here. But at least let me show how from the first line you go to the second, which is somehow in computation in the same spirit, but less heavy. Okay, suppose, all right. So suppose I want to prove this equation with this inequality with the star given the one which is just above. So this now becomes really a question of writing down the sum, approximating with an integral, and then solving the integral. And then you will see the log-log appearing. Okay, so before doing that, let's look more closely at this expression. So you have the expectation, again, you have the nonlinearity, but only the first Fourier component, the zero Fourier component, sorry. Then you have this inverse, and then again, the zero Fourier component. So let me recall how the nonlinearity looks like. the nonlinearity written in Fourier space is a sum over the momenta L and M. There is this prefactor which is important, but it's not random. It's something like KL LM there was a cutoff that tells you that all the momenta are smaller than L. Oops, there is no space here. I'm sorry. And then it was times something like L2 M2 minus L1 M1. So it's something totally explicit. And then times the Fourier component L times the Fourier component M. Well, okay, on the left-hand side I have H, on the right-hand side of eta, this is just a typo. These are the components of the Fourier components of the Gaussian free field. Okay, so if you want, this is eta. And this is also eta. Okay, so this is the nonlinearity. Now we want only the zero Fourier mode. So you're just taking the zero Fourier mode. It means, what it means is simply that you have, in this whole sum, you have to select only those L's and M's whose sum is zero. Okay, so this double sum becomes a single sum. When you take the Fourier, the integral over the torus of this stuff. Okay, this is not well written. I'm sorry. I should have. I'm sorry. Okay, if I want to take the expectation in dx, here I have to multiply by e to the I kx plus I lx. Okay, so this is written as a function of space. No, this is now correct. Now, when you integrate with respect to x, of course, this will kill all the component unless L, and sorry, I think it's, I'm feeling a bit tired. So it's not a k, it's m. There is m and there is L. Okay, now it's correct. When you integrate with respect to x, this kill all the components except if m equals minus L, and this is what happens here. You are left with a single sum over L of k L, L minus L, eta minus L. Okay, very good. Now, this is an expression. Now you want to put it back here. And now you, okay. And now you want to take, I mean, you want to go back to this expression. Sorry, the expression is here. You have to take expectation of this thing we have just computed times the inverse of mu L squared minus L0 plus V3, etc. and itself. And now you want to replace this V3 by this bound here. Why we want to do that? Because then the computation becomes a very simple sum, because now we are in Fourier space. Since this upper bound is diagonal in Fourier space, this just becomes a sum over L of something. And if you put back things, maybe let me write down in a oh, I have reached the maximum page count. That's great. Okay, so when you put back this expression into this sum, what you get is you have this coefficient KLL minus L, which appears twice because it is in this end here and in this end there. So you get it squared. Now you have in the denominator, you have L to the power 4. Where does that come from? When you take the expectation of eta L, eta minus L, it's the Gaussian random variables of variance 1 over L squared. So when you take the expectation, you get a 1 over L squared and another 1 because you have 4 eta things. You have 4 etas. So each n contains 2 etas. There is 2 other etas from the other n. When you take the expectation, you get the square of a variance. So you get the 1 over eta, 1 over L4. And then all this purple thing in the middle just comes from this inverse operator. So if you have the inverse, so you have 1 over. It's diagonal, so you can really take 1. It's just a fraction of numbers. There is the mu L squared, which was there. Good. It ends up here. There is the Laplacian. There is the generator of the linear equation that gives you L squared. And then there is this V3 that you use the bound and gives another L squared times the log. Okay, so it's a very explicit sum in a sense. It's a sum over Z2, etc. Okay, now I've rewritten this sum. It's just rewritten for you. This ratio here of K, L, etc., is essentially bounded above and below by 1. So you forget it. But what remains from that is the cutoff that tells you that the momenta are at most of size L, not L squared. So what you are left with is 1 over L squared the sum over the momenta, so L is in Z2, but the norm of L is smaller than L, big L. And then this 1 over mu plus L squared over big L squared times 1 plus log of similar thing. And now, no surprise, when we take the size, when we take the cutoff to infinity, this integral becomes, this sum becomes an integral. You're just left with this two-dimensional integral. So x is still on R2, but the norm of x is restricted to be at most 1. And you have this two-dimensional integral. And now you're done. I mean, essentially, this you go to polar coordinates, this becomes essentially explicit, and you get the log-log divergence. Okay. So these are this just gives you a flavor of the type of approximation or type of estimates that come out when you want to prove really the result. I mean, in the first step is quite easy. As you can imagine, when you go to the generic step, it's quite messy because we cannot find the primitives of the things explicitly. But I mean, this is life. And so I hope this gives you at least an idea of how we get at least the first non-trivial bound. And let me check if there is any question. No. So, and I would like to end, maybe I have like 15 minutes left or something like this. I would like to end on a more light note. I would like to explain, I have already told you several times that we have some heuristics to justify delta equal 1/2. Let me show how this goes. Because somehow I find it very surprising that the heuristics is new. I mean, the type of approximation on which the heuristic is based is not new. It's an argument that the physicists have been used since the 80s. It's called mode coupling approximation, but somehow it was not noticed that applied to this problem, it should give a logarithmic divergence. So let me explain how this works. Of course, it's a heuristic. It's not just I'm forgetting details. At some point, there is really an unjustified approximation, but I will tell you exactly where it happens. Okay, so let's restart with our object we work quite often about in the paper more than in the slides. So H is the solution of the equation. And U is just the solution of the equation where you apply minus the Laplacian to the power 1/2. Okay. And it has the advantage that at stationarity, expectation of ux, say t, u y t is delta. This thing is delta correlated. So while the H itself is a GFF, which is sort of already a more complicated object, has this logarithmic correlation and so on, it's this U itself is just white noise, so it's delta correlated. But on the other hand, you can reconstruct, apart from the zero mode, you can, studying U or studying H is the same thing. I mean, you can reconstruct it. Okay, and so let me recall that already when I gave the definition of the diffusion coefficient, I had introduced this so-called form, how is it called? Structure function, I think. Anyway, S of xt will be the expectation of UTX, U00. So it gives you some correlation, space-time correlation, which at time 0 is just a Dirac delta. Okay, so the first thing, it's convenient to work in Fourier transform. You take Fourier transform. So this S hat now of K and T is just the expectation of the product of the kth Fourier component of U at time T and the minus kth one at time 0. To get this, you just use translation invariance of the process. Okay, now for the linear equation, this S hat is totally explicit. Actually, it's essentially an equality. It behaves like exponential of minus k squared t, where maybe there is 1/2, okay? Where this k squared just corresponds to the Laplacian. And the fact that here you have exactly t tells you that you have normal diffusion. Now, okay, so the heuristics is of the following type. Somehow one assumes that maybe with nonlinearity, this form is modified as it becomes, instead of being e to the minus t k squared, this t becomes t times log t to some delta. And the point is to try to write down a self-consistent equation for S hat, which allows to identify the unique delta for which this can happen. Okay, so the way it works, as in many cases, you start out with an exact identity. Here, up to some point, there will be no approximation. It will just happen in 2 slides. So initially, you just take the definition of this S and take the time derivative. Okay, so as you can imagine, when you take the time derivative of this object here, the time derivative will act only on this part here. So you just get the derivative of the equation for U, which contains a Laplacian, which contains a white noise, and which contains the nonlinearity. Okay, so you use the definition of the equation for U, and you get two terms. You get the terms which is sort of diagonal, so you get dt s hat of kt equals -1/2 k squared s hat of kt. This is the term that comes from the Laplacian, is the term that you would get for the linear equation. And for the linear equation, that would be all. Okay, for the linear equation, this is all we would get. And then you have a closed equation for S. You solve it and you find this what I've written here. Okay, so for the linear equation, that's it. Now, for the nonlinear equation, you get something more. And of course, unfortunately, but it's totally expected, that the extra thing you get is not a function of S itself. So in the end, dts is not expressed as a function of S, so you don't get a closed equation for S that then you can solve and approximate or something. You get a non-closed thing, but it's for the same reason as this equation for phi, for the second cause, was not a closed equation. Okay, what you obtain, I don't write exactly what you obtain, but at least as a type of structure, you get you get a lambda squared, which is good, so it disappears if lambda is 0. You get a k squared, okay, which is nice because it has the same structure as the linear term. And then you get something more complicated, that is an integral, a time integral from 0 to t. There is this prefactor here, which is totally explicit, e to the -1/2 k squared t minus s. It's just a semigroup of the linear equation. And then you get an expectation here. It's an expectation that contains, so you see in the definition of S is an expectation of a product of 2 Fourier modes. And now this expectation here contains 4 of them. Okay, so this is why it's difficult. You have 4 Fourier components of U. 2 of them are computed at time S. So here there is an integral in ds. 2 of these components are computed at time S. 2 of them are computed at time 0. They depend on certain momenta, and these momenta are summed over. I don't write the exact expression, but already from here you see that what do you do at this point? Well, you have an expectation of the product of 4 things. How can I write it as something involving only S, which is the expectation of only 2 things? So up to here, if I had written down the precise formula, it would be just an identity. There would be no approximation at all. It's at this point that this famous mode coupling approximation is made, which can look very arbitrary, but if you think of it for a while, it's not really so. So the approximation that is made here is that when you have this product of 4 variables for momentum, so for Fourier components of the equation, you treat it as if they were Gaussian variables. So it's really Gaussian approximation. So, and now you can apply what is called this Wick's rule. So if you have an expectation of a product of many Gaussian variables, an even number of them, otherwise it's 0, you can write that as a sum over all the pairings of these 2n variables of the products of the corresponding covariances. So if you have an expectation of U1, U2, U3, U4, you write it as expectation of U1, U2 times expectation of U3, U4, plus the same thing with 1, 3, and 2, 4, and 1, 4, and 2, 3. You are just, if you have 4 of them, you have just four possibilities. If I had many, I would have many factorial possibilities. Okay, of course, so here is really an approximation, but the idea behind that is that, well, okay, we expect maybe the process not to be Gaussian, we expect it to be modified, but maybe at least if lambda is small, the modification should not be major. And since the linear equation is Gaussian, we can hope that the nonlinear equation, at least for small nonlinearity or something, is still kind of Gaussian. So anyway, this is what one does. And if you do that, clearly now you get a closed equation for S, because the right-hand side now, just involves 2-point correlations. And what you get in the end is the following. On the left-hand side, you have dt plus k squared over 2 of s hat. And on the right-hand side, you get lambda squared k squared times this integral from 0 to t, which was there before, it remains, this explicit factor. And then, well, a sum over momenta becomes an integral. I mean, this is okay. And then there is a product of two functions s. So the difference with respect to the linear case, in the linear case, you had a closed equation, which is linear in s. Now for the nonlinear case, you get modulo this important approximation. You have a nonlinear equation, sorry, a closed equation for s, which now is nonlinear. In the right-hand side, you have a convolution of this s. Okay, and at this point, anyway, I mean, this is not an equation you can solve explicitly, but at this point, it is done in the sense that what you do is actually you care about this equation only for k small momenta, which means large distance, and for large times. And you remember, okay, so for small momenta and large times, for instance, this k is irrelevant, it drops. This factor here you approximate with 1 because k is say 0. The k in front you keep, otherwise you get 0. We wouldn't tell you anything. Okay, so you end up with this approximated equation. And now you remember the ansatz that consisted in saying, well, okay, for the nonlinear equation, let's try a solution of the type s of kt of the type e to the k squared times t, which is the thing you get for the linear equation, plus a log correction, t log t to the delta. And now there is the only computation to be done is to say, well, okay, is this possible? Is this a solution of this equation, at least after all these approximations? Yeah, just a second. Yeah, right. The two are, yeah, I see a question, but Giuseppe is answering, but I can, yes. So, but anyway, I can also explain that for everyone. So yeah, you're right. So you had here, the four terms were like u l s, u minus l s, u say minus l prime 0, or maybe plus l prime 0, and u minus l prime 0. So now you have to take the contractions in the VIX thing. For instance, you contract this guy with this other guy, and this gives you s, I mean large S of L S. Okay, so unfortunately, it seems like I cannot add another slide. This is an interesting thing. So let me just delete this one. And so, okay, so you have something like expectation of u hat ls, u hat minus ls, u hat of l prime 0, u hat of minus l prime 0. This is what you get. So now, for instance, suppose you contract this guy with this other one, and this with this other one. What you get is s of l s. Well, when you contract two things, the momenta are forced to be one the opposite of the other. So this one thing that follows immediately from translation invariant is that S prime, say, is 0 unless SL equals minus M. This is just from translation invariance of the law. Okay, so here when you contract like this, you get S of LS times S of minus LS. Okay, it does, yeah, okay, good. Very good. Right, so the idea is, now we have done various approximations. The most serious one is the Gaussian approximation. Maybe it's the only one. And now what you do, well, we try a solution of this form. So, I mean, you have a left-hand side, which is this dt plus k squared s hat. You have a right-hand side, which is this. Okay, when do they coincide? Well, now you need to do a small computation, which I will not do. You take this form here, you compute this integral, it's just a convolution. This integral is just a convolution. And miracle, well, not so miracle. At the end, what you get, left-hand side gives you minus k squared log t to the power delta, and the right-hand side gives you minus k squared log t to the power 1 minus delta. So, okay, so this is possible only if delta is equal to 1/2, clearly. Okay, so it's as simple as that. And if instead you do the same thing for AZEP, For ASEP, the way the 2/3 was guessed was to replace, to modulo other approximation, to write down an SPD which should mimic ASEP, which looks a bit like AKPZ, but it's not it. And if you, for that SPD, you do the same heuristics, you end up with here delta over 2. And then the solution is delta equal 2/3. Okay, so it's this delta over 2 of difference that really makes the difference in the end. And the fact that there is a delta over 2 and not a delta. So I mean, this difference in this computation reflects in the fact that all these integrals or sums that appear here are quite different from those which appear for the ASEP. It's really, the structure of these sums is really quite different, of the operators themselves is really quite different. Yeah, I think I finished essentially on time. I wanted to finish with these heuristics for those who remain, because I think it's worth seeing. And yeah, I would stop here, and feel free to ask questions if you wish.
Okay, well, let's all thank Fabio.
Thanks.
And we do have time for questions. And let me start with one that I have. So the work that you mentioned of Landim, Costel, Solomon-Hofer, and Yao, and Yao's work, they worked on a lattice model. They worked on ASA, and they were able to do a similar sort of decomposition in the equilibrium measure.
Yeah, there is kind of an analog of this Gauss decomposition.
That's right. So in a sense, by taking the cutoff in Fourier space, you lattice, you take some regularization, but you can't, are there lattice regularizations that you can work with that might have a property that you can?
Yeah, I don't know. I mean, yeah, it would be nice to have some lattice regularization that preserves a Gaussian measure, for instance.
That's right. Well, or in the case of ASAP, it's not a Gaussian measure; it's a Bernoulli measure, right?
Yeah, so, but here somehow I would say that if you take a regularization that such that then the stationary state doesn't look like the one of the continuum measure, then it's then probably everything becomes much more difficult. So I think. The answer is no. I don't know of regularization for which we could do things. I think if one found a regularization for which preserves as a stationary measure something, well, maybe not exactly Gaussian, but it's at least something like a grad phi interface model with local interaction potential, that would be a good candidate.
So some of the discrete models that we've worked with, they
right, but
something of this flavor.
Yeah, right. But then the problem is, okay, let me say, we didn't try to apply this technique there. Actually, it's what we are aiming at doing now. But this decomposition of the generator into symmetric and asymmetric part, I think it's much less clear there. And also the stochastic calculus tools are less. I mean, even for the ASEP because of this discrete structure, they had to struggle with important problems like removing the hardcore. I mean, this discrete structure really poses new difficulties. We have not really tried to apply it for, say, I don't know, domino shuffling or whatever of these other models, but what I think is that there will be additional, the discrete structure will actually be pose additional difficulties. This is my guess, but.
So the beta-rated log bound that you mentioned.
Again, sorry?
Seems to me, so somewhere in your talk, you mentioned this double log bound.
Yes, this first bound that this one, you mean this?
That's right. So this calculation seems reminiscent to me to if you would just take the equation and apply Picard iteration. If you just blindly take the linear equation and insert it into a quadratic term. And you calculate something like the variance. You come up with something.
Yeah, that's possible. By the way, if you want only this first bound, you can obtain it. You can forget this iterative thing. You can just use a. I don't think it answers your question, but maybe it's also interesting to mention. You can. There is also a variational representation for the say the diffusion coefficient, and you can get this first bound easily variationally. Whether it corresponds to a Picard iteration, now I cannot say. I would have to think of it. Yeah.
Okay. Thank you.
Welcome.
Okay. Unless there are any other questions, we'll break. Let's all thank Fabio once more for this lecture and for the 3 lectures in total, which were very nice. So what I'm going to do is I'm going to close out this session, and then I'll start the new one, which will resume in just under half an hour. So you can join anytime between now and 45 after the hour when I think Hugo will do his second talk. Okay, so I'll see you guys all in a little while. Bye.